In the previous module, we have stated a very important result, namely the Gibbers-Satterthwaite theorem, which says the following: that if you have 3 or more alternatives and the social choice function that we have considered is onto and strategy proof, which essentially means that it is any of this statement. So either it can be Pareto efficient or strategy proof, or unanimous and strategy proof, then it is necessary and sufficient that F is dictatorial. So this is a very crucial result, and we are going to prove it. But before we start proving that, let us look at what are the implications. So what are the some side notes of this result. So the first remark that we'll make is that if you have 2 alternatives, then this theorem can be circumvented. And the reason for doing that is a very simple rule, like the plurality rule, which we have discussed in the previous modules, with a fixed tie-breaking rule, can actually be strategy proof onto, and quite naturally plurality is non-dictatorial. So if we have only 2 candidates in an election, then we are actually safe. We don't really have to worry about this very restrictive result of Gibbers-Satterthwaite. The second remark is that notice that the domain, the social choice function that we are considering, has this domain of the complete preference. So remember that we had this social choice function which was mapping the set of all possible orderings, all possible linear orders of all the players to one alternative, to the alternative space A. Now what does that mean? So let's say if we have m candidates, then all m factorial possibilities, all m factorial linear orders over those candidates are feasible. They can exist in the social choice, the domain of the social choice function. We will very soon see a restriction where all these possibilities, m factorial possibilities, are not available for the in the domain, and then we can actually show that there exist interesting positive results. In fact, there are mechanisms which are strategy proof onto and non-dictatorial. So GS theorem critically depends on this on the assumption that the domain is the full domain, as we will call it. If the preferences of the players admit indifferences, so here we are considering only linear orders, but if there are indifferences, then in general Gibbers-Satterthwaite theorem might not hold. But as we'll see in the proof, that we are constructing certain kinds of preference profiles. If those kind of preference profiles are admissible even in those indifference domains, then actually we can get back the Gibbers-Satterthwaite result again. And the fourth remark is about cardinalization. So GS theorem will hold as long as this all possible rankings are feasible. So so far we have considered the preference rankings are only ordinal ranks, but if you think of that there exists some cardinal ranks which induces all these possible linear orders over this preference, over these candidates, then the result of Gibbers-Satterthwaite will again hold. So it is actually is generalizable to the setting where we have cardinal preferences instead of ordinal preferences. So these are the few points which is useful to remember. So let us now get into the proof. In this proof we are going to follow a direct approach, which is due to this paper by Sen 2001. At the end of the module I'm going to give you a complete reference of this paper. It is very instructive to read that paper, because that gives this the whole proof of Gibbers-Satterthwaite, and it's quite compact. Now what we are going to do in this module is to prove this result for 2 voters, so n equal to 2, and the number of candidates can be anything. It has to be at least 3. The general proof for more than 2 voters applies induction on the number of agents, and that we leave for an independent reading. So to prove the result for two candidates, the plan is to prove these results in steps, and the first step will be to prove this lemma, which actually shows that if a social choice function f satisfies these two properties, onto and strategy proofness, and we have only two voters here, two agents here, and at least three candidates, then the social choice function must be either the top alternative of player 1 or the top alternative of player 2. Now if the top alternatives for these two players are the same, then we know from the corollary above that ontoness and strategy proofness is equivalent to saying f is strategy proof and unanimous, and unanimity will actually give us the fact that the social choice function should be the same. If the top alternatives are same for both these players, that should be the outcome of the social choice function. Now we'll have to show it for the other cases. So let's say when the top alternative of player 1 and top alternative of player 2 are different. So for player 1 it's A and for player 2 it is B. Then let us assume for contradiction that the outcome is neither A nor B, it is something C. And this is the place where we are using the fact there are at least three alternatives. This construction couldn't be done if we had two alternatives. So to prove this, we construct the following preference profiles. So of course the original preference profile is P1 comma P2, and there the top alternative for player 1 and 2 are A and B respectively. Now I have constructed some other preference profiles using by appropriately choosing the position of A and B in this case. So let us look at what happens when we apply these properties which are given in the lemma to these preference profiles. So just to remember that the outcome in this preference profile is C, that is by assumption. Now what we can see is that this the outcome in the second preference profile must be either A or B. And why is that? Because this preference is, by the corollary we know that the social choice function is also Pareto efficient, and if you look at in this profile, A is on the top most position and the second top position for these two players in this preference profile, and therefore all the other alternatives except A and B are Pareto dominated by A. And because the social choice function is Pareto efficient, it cannot pick any of those alternatives. It can either pick A or B. Now let's consider the case when this alternative is B. So if the outcome is B, then you can see that player 2 now has a reason to manipulate from P2 to P2 prime. Why is that? So you know that in P2 the preference, the topmost preference for player 2 is B, and C lies somewhere below, and the social choice outcome is actually C, which player 2 prefers less. Now if it moves to this preference profile, for player 2 the reported preference is different, then it gets a better alternative because it now gets B, which it prefers more than C. So clearly this cannot happen, this outcome cannot happen, because then the social choice function becomes manipulable. So the only possibility left is that this is going to be A. So therefore the outcome in this preference profile is going to be A. And you can see that this P1 prime and P2 are essentially very symmetric to this preference profile here. So therefore the outcome here, in a very similar argument, you can say that this is going to be B. Now you can take a look at this preference profile, and the policy that we are going to use is look at the transition from here to here and the transition from here to here, and apply the condition of monotonicity. So what is happening here, you can see that the position of A is getting weakly better off. Essentially it is getting this, it is remaining the same. So the if condition of the monotonicity property still holds. So if A is the outcome here, then A better be an outcome here as well. That is the requirement of monotonicity, which is equivalent to strategy proofness. But here also you can see the same thing happening for B. B's position is getting weakly better off, remaining the same. So if the social choice outcome is B here, then it should also be B here. And there is a conflict here. It cannot be same at the it cannot be the correct at the same time. So what we have assumed here is actually incorrect. So if we assume that the outcome is C, then we reach a contradiction. So the outcome can be either A or B, nothing other than A and B. So that completes the proof of this lemma. Now let us look at the following statement, which can essentially be thought of as the result, the Gibbers-Adderquate result or the dictatorship result for two players. So what does this lemma say? It says that if you have three alternatives and you have two players, and F is on to end strategy proof, and let us assume that the top alternatives for player 1 and 2 are different, and we have another preference profile where the top alternative of player 1 becomes C and that of player 2 becomes D. Then this condition, these two conditions hold. So if the outcome is the top alternative of player 1, then it continues to be the top alternative of player 1. If it is the top alternative of player 2, then it continues to be the top alternative of player 2. So this is the meaning of this statement. Let us look at the proof now. So if you have C and D to be identical, then we have argued before that the unanimity will prove this lemma. Therefore, without loss of generality, we can assume that C and D are not the same. In this table, we have enumerated all possible cases where C is not equal to D. So you can check that this is the exhaustive case. So all these cases where C and D are different are covered here. What we will do, we have ordered it in a way such that we can reuse some of the previous cases in the later cases, and that is the reason we are proving in this sequence, very similar to what we did for the arrows impossibility result. Now we are going to prove only this implication. The implication for the second is actually a symmetric implication, so we can consider player 2 to be player 1 and apply the same result as here, and that will give you the second implication as well. We are going to assume that the social choice outcome is A in the preference where in the preference of P, where the top alternative of player 1 is A. That will imply that the social choice outcome for P prime would be equal to C. Now let us look at cases one by one. So case 1 first. So here the top alternative in P prime is A for player 1 and B for player 2. So this is the P prime. Now we are going to construct another preference profile, P hat, where the alternatives are looking in this way. So A is on the top and B is the second top, and for player 2 is the opposite. Now we know because of the previous lemma that even in this P1 prime, P2 prime, the outcomes will be one of these top two alternatives. Now let us assume, so what we need to prove is that it should be equal to A. Let us for contradiction assume that this is B instead, and we will hit a contradiction. Now if this is B, so let us assume this is B, and we already know that the outcome is A here. Now you can see that if we do this transition from here to here, A was somewhere below. I mean, it might be at this the very next position to B, or maybe somewhere down. But what we have done in this P prime profile, P hat profile, is to drag that A to the second highest position. So in this profile, what has happened is the relative position of A has become weakly better than what it had in the profile P. So using monotonicity, we can conclude that the outcome here should also be A. Now you apply the same argument for this preference for the alternative B. So here B has been dragged to the second top position, so its position has also become weakly better. So if we apply this transition here and apply monotonicity, then we can conclude that this outcome should be equal to B, and that brings us to a contradiction. So therefore the outcome, so this implication, this assumption is not true. So the f of p prime must be equal to a. So we have proved case 1. So for case 2, what we are going to assume that we have so player 1 in this p prime has a different alternative, which is neither a nor b. The second player's alternative does not change. Top alternative does not change. Now we all again know that this p prime must be either this c or b because of the previous lemma, and we are going to assume for contradiction that the outcome is b and not c. Now we are going to construct a p1 prime where we have the topmost alternative for player 1 is c and the second best is a. Now you can apply in a very similar way in this implication for the transition from p prime to p1 hat comma p2. And what we can see here is that player 2's alternative, top alternative, hasn't changed, and player 1's top alternative hasn't changed. So this is the identical situation of case 1, and once we have this, we know that because by assumption this outcome here is b, that's what we have assumed, then case 1 says that the outcome should be b here as well. So that is the implication. Now you can see that there is a reason for player 1 to deviate in this preference profile in this p1 hat to p1, because we know that the outcome here is a and here the outcome is b, which is lying below c and a here, so somewhere below here. Clearly player 1 prefers the alternative a more than b, even in this profile. So therefore if p1 hat happens to be the true preference of player 1, then player 1 better report it to be p1, which at least gives him this outcome a, which is preferred more than the current outcome, which is b. So that actually contradicts to the fact that this function, social choice function f, is strategy. So that proves case 2 as well. Let us look at case 3, where we have now an alternative for player 1. The top alternative is neither a nor b, and for player 2 in this p prime, we have a alternative d, which is not equal to b. Now, as usual, we are going to assume that the outcome here is not c, rather it is d. That's the assumption here. Now if we go from this transition, and we have also written down a different preference profile, which is p hat, and now if we look at this transition from p prime to p hat, what we see is that the outcome should be equal to b, and that is due to the fact of case 2. So what is case 2? We had the first transition, so player 1's preference and the top preference is changing, player 2's top preference is not changing. In this proof of, you can see that the case 2 can also be proved in a very similar way for player 2. So when player 2's top alternative changes and player 1's top alternative does not change, then if the outcome is the top alternative of player 2, then it should continue to be the top alternative of player 2. So we are taking that liberty of that generalized result of case 2. So here we are using the fact that if in this preference the outcome is d, that is the top alternative of player 2, that should be in this preference profile, the outcome should be b, that is due to the case 2. And similarly here the outcome is a, and you see that for player 2 the top alternative is not changing in these two cases. So using the same case 2 again, we get that this outcome is c. And now because c is not equal to b, we arrive at a contradiction again. The rest of the cases is essentially cleverly creating these preference profiles and using the ideas of this contradiction. So if we have this case where c, the top alternative, is the same as the top alternative of player 1 here, and only player 2's top alternative changes to d, which is neither a nor b, and by assumption the top alternative the social choice outcome at p prime is actually equal to d. Then we look at this transition. We again construct a new p hat which has a and b as top. From p1 to p hat, we see that this alternative for player 1, the top alternative is not changing, and here the outcome is d, so therefore here the outcome should be b according to case 2. And here from p to p hat, we know by case 1 the top alternatives are not changing at all, so therefore it should be a. And because a is not equal to b, we again arrive at a contradiction. Similarly, when you have the top alternative of player 1 is b, which was the top alternative of player 2 in the original profile, and again we assume for contradiction that d is the social choice outcome here. Then we construct this preference profile. Actually this should be so it should be a essentially. So yeah, for player 1 the alternatives are actually getting changed, so therefore since the outcome here was d, it should be the outcome in this preference profile as well, using the property of case 4. And again we are using the liberty that you can apply case 4 even for player 2 as well. And similarly, when you have this transition, so here the outcome is a, which is the top alternative of player 1, and here for player 2 the top alternative changes, and for player 1 the top alternative does not change, and therefore the using case 4 we can conclude that this outcome should be a here, and that is again a contradiction. So the case 6 is very similar. You can actually see this the argument here itself. We have created a few more preference profiles. So the outcome here we are going to conclude. So assume that this is a for contradiction, and let's say x is some alternative which is neither a nor b, and we have constructed these two preference profiles in this way. Now if we look at this transition from p prime to p1 hat, so this one, so this transition here, then using case 1 we can conclude that this outcome will be a. So look at case 1, there we have the top alternatives to be same for both these players, and when we apply that we get a as the outcome here. Now if we also look at this transition from p to p1 tilde and p2 prime, then what we can see is that using this case 3, so let us go to the case 3, we had the second alternative d, which is not equal to the top alternative of player 2, and the first alternative has changed such that it is neither a nor b, and that is exactly what is happening here. We have x which is neither a nor b, and we have got another alternative which is a, which is not the same as the top alternative of p2. So case 3 applies, and we conclude that the outcome here should be x. Now if that is the case, then we can see something is going wrong between these two preference profiles. So what is happening here is that here player 1, so player 2's preference profile does not change between these two preference does not change in these two profiles. Only player 1 changes, and in player 1 if he reports, so if player 1's true preference is p1 hat, the outcome is a, which is lying somewhere below these two things. In particular it is below x, and therefore the outcome that the social choice function gives is essentially worse than x, which it prefers more. And if he misreports, if player 1 misreports his preference to p1 tilde, then clearly he gets a better alternative, because here the outcome will be x, which it prefers more than a, even in this preference order. So player 1 has a reason to manipulate, and that contradicts to the fact that f is strategic. So we have actually exhausted all the possible cases for two players, and therefore the proof for this Gibbers-Adderquate is done for two agents. For more than two agents, look at this proof from this paper, which is titled A Direct Proof of Gibbers-Adderquate Theorem. It uses the induction on the number of agents. The proof is just lengthy, but it uses the same ideas that we have proved here.